Yes. So Friday we talked about holes in our graph. That's what I want to talk about today. One more example of. Then we'll get into slant asymptotes. So far we've talked about every one of our graphs having a horizontal asymptote. Because we talked about the situation where the degrees are either, the leading degrees are either the same or the denominator is bigger. Well, if the numerator is bigger than the denominator, then what takes place? And that's what we'll get into by mid to the end of today. But the first example, I just want to graph this just as if we were doing the whole thing from scratch. So remember, our goals are to determine horizontal asymptote, vertical asymptote, holes, x-intercepts, y-intercepts, and then do we cross the horizontal asymptote? Okay, we're going to ask or determine those six things. Okay, first thing you have to do is factor. So this one isn't too bad, where you just got to factor out x squared out of the top. Leaves you with x minus 3. Sorry, x minus 2, thank you. And x minus 2 on the bottom. Okay, so what we normally look at is denominators equaling 0, right? And we think we should get vertical asymptotes there. On Friday, we mentioned the idea that no longer do we want to think that. We want to think that the denominator is always going to provide us locations of discontinuity. We have to decide whether they're vertical asymptotes or if they're point discontinuities. Okay? And in this case, because there's that common factor, they are point discontinuities, right? Okay? And that's what we call a hole. So you're going to have a hole at x equals 2. Okay? Now I know I skipped the horizontal asymptote. If I look at this, to do the horizontal asymptote, we have to look at those, right? Okay? And if we scroll up, it says, that calls this one M. I think maybe that calls it N. I'm not sure. It doesn't matter. Let's call it N. So here it says if N, which is the numerator, is greater than M, which is the denominator. And I'm talking about the leading degrees of the numerator and the denominator. If the top is bigger than the bottom, then you have no horizontal asymptote. Okay? And right now, we're just going to say no horizontal asymptote and move on. Okay? So I'm just going to say not applicable here. Okay? Vertical asymptote for the same reason. I mean, these cancel, right? Those were the hole. You have no vertical asymptotes. When those cancel, we do end up with x squared. Okay? So when I have a rational function where terms cancel, when you find x-intercepts and y-intercepts, you're going to want to go from the reduced version. Okay? So if I look at x squared, what are the x-intercepts for x squared? Isn't it 0, 0? Isn't the origin? That's where the vertex is. And if that is an x-intercept, it is also the y-intercept. Okay. Because we don't have a horizontal asymptote, there is no way to cross it. Yes?
I don't understand why you don't have horizontal.
So horizontal is when we look at these two and compare them, right? So when I compare them, I get x cubed over x, and that's going to reduce to x squared. So that is the thing that is, because remember, horizontal asymptotes, slant asymptotes, oblique asymptotes, those types of things, we're only interested when x gets really, really big. So if x is, let's say, 10, then that goes to 100, right? X squared. If x equals 100, then this becomes 10,000. If x goes to 1,000, this becomes 1 million, right? So are these values here, are they approaching something specific? Are they converging to one number? They're getting bigger and bigger and bigger, right? So they're increasing without bound, so they don't have a horizontal asymptote. If we would have a horizontal asymptote, these numbers would approach one specific value. It's kind of like up here when we did this one here, we had, so the 1 over x was that comparison of the leading terms. So when x equals 10, this approached 0.1. When x was 100, it went to 0.01. When x was 1,000, it's 0.001. 10,000, 0.0001. And then these numbers here, they're getting closer and closer to 0, aren't they? And that's why that becomes a horizontal asymptote thing.
So you can, when you're looking for it, you can look at the simplified form, like do that on x squared, and then only look at the standard form from A to that out. So you look at x squared for everything, then you double check it for each.
I'm going to, so every time I find a horizontal asymptote, I'm not looking at that for horizontal asymptotes. I'm always comparing this for horizontal asymptotes. Always your leading degrees of the original function. Then vertical asymptotes, you're looking at the factored version, okay? But if there's cancellation, then the whole overrides the vertical asymptote. We thought we would have a vertical asymptote at 2, right? But because there was cancellation, the whole overrides that. And that's because of the way we evaluate what's left over here when we cancel and we evaluate close to 2. We don't shoot off to positive or negative infinity like we do near an asymptote. Basically what happens if I put like 1.9 in, 1.99, or if I put 2.01, 2.001, evaluating those numbers for that thing are going to give me y values very, very close to 4 every time instead of increasing to positive infinity or negative infinity. This here, this reduced version, that's where I'm going to look at that stuff. X-intercepts, Y-intercepts, determine whether I cross the horizontal asymptote or not. If we go through and we graph this thing, okay, the reduced version of x squared is exactly the same thing as what we start with, except for 1 point, okay? So what I'm going to do is I'm going to graph x squared, which has a point at 0, 0, 1, 1, negative 1, 1, negative 2, 4. Okay, now when I get to 2, 4, think about this. We had a hole at x equals 2, right? Okay, and that was a hole for that function right there. That function that we started with in x squared are the same at every single point except for 1. The one that they're different is when x is 2. That's the hole here. Does that make sense? If x was 2 over here, what would be the y value? 4. So if they're the same everywhere else, then 2, 4 is going to be the same as, I mean, I can't deviate away from, I can't graph this thing and say, okay, that's the graph for the original, and then maybe, at 2, 4, like the point goes up. I can't, that 2, 4 there, because of the way of every other point being the same as this one, identical to this one, I can't just at 2, 4 have something just completely unexpected there in that graph. Does that make sense? I don't know a better way of verbalizing that. So in regards to trying to find the actual location of the hole, you take the x value that the hole existed at, and you plug that into the simplified, reduced version, and that will tell you the y value. And the reason I can't plug it back into this one, what would happen if I plugged it back into this one? I would get 0 over 0, which is undefined, right? So then if you ever accidentally do that, that hopefully signifies, oh, can't put it in that one, put it in the reduced one. okay? And you get 2, 4. What that tells me is that 2, 4 is on x squared, which we knew about, but on the original function, it should be an open dot instead of a closed dot, meaning that that point is undefined there. So I'm going to graph my parabola like that. Okay? No technology provides that hole very conveniently. Okay, now we found some stuff in the last class with Desmos that is nice. So I'll see if we can pull that up real quick. No. So if I have x cubed minus 2x squared over x minus 2, would have anybody looked at that right away initially and said, that's a parabola? You would have thought that, right? Okay. When we graph things, that's exactly what we get, right? It looks just like x squared. Okay. However, if I click on this graph, obviously it shows me my x and y intercepts, and I'll always do that. But if I go to 2, 4, and click on that, see how it actually tells me it's undefined there? It actually makes it an open dot. Okay, it would be nice, like if you graph, once you hit enter when you graphed it, if it automatically put the open dot there. Yeah, but programming doesn't do that. Okay, if we wanted to do this in GeoGebra, it doesn't do that for us. We actually have to, so again, just looks like x squared, but I can't come up here to the point and click on it. I actually have to ask it to evaluate at where I think the hole is, and it will then tell me it's undefined, which guarantees or confirms to me that there was indeed a hole there. Okay. Your TI 83s and 84s, if we look at those. If we go x cubed minus 2x squared divided by x minus 2. All right, so most of our windows, or not windows, tables, are going to be set up initially. If you've never messed with this thing right here, that's kind of the default that these things are like shipped with. So when you graph it, obviously, it's going to take a little bit of time because it's evaluating. So if I were to graph that compared to just x squared is going to graph like very fast. So let's just go and just compare these times. So did you guys know you can highlight the equal signs and it will only graph the ones that are highlighted? Okay, so I can type in as many functions as I want. If I go through and I highlight, hit enter on the equal sign, the ones that are shaded are the ones that are going to be graphed. So if I go graph, I guess that wasn't really all that different, but they are both the same function. Okay, see if it graphs the blue on top. Okay, so you see it, they're the same. Okay, now what would be nice is if at 2, 4 it would skip a pixel or something, right? But it doesn't do that. The way that I'm going to have to realize that I've got a hole here is I'm going to have to hit second and then go to my table. And you can see what your table does. Okay, so the blue graph was the original rational function that we typed in. I like the color version of these calculators other than the monochromatic version, because it reminds me which function was what here. If you just got the monochromatic, they're all gray, and you just got to keep track of it. But at 2, it says we have an error, right? Okay, and basically what that tells me is that that is the location of the hole. Okay, the red graph was the reduced version that I typed in, right? So you see that at 2, 4, that's where the error occurs, and that's where you have then the hole. Does that make sense to everybody? Now, if I had, so that's nice, but let's say that we had a function that looked like, something like x minus a third, let's just say times x over x minus a third. Okay? Where's the hole going to be there? X is going to be a 1/3. It's where these are zeros, right? So where the canceled term or the common factor is equal to 0, so 1/3. And what I'd be left over with is just x, right? So when I plug that back in, I'm going to plug it into the reduced version, and I get back 1/3. So I'm going to have a hole there. So the graph of x times x minus a third over x minus a third is just the line y equals x. But it has a hole at 1/3, comma 1/3. Okay? Let's see if that is confirmed. So x times x minus a third I don't like the TIA3 for the fact that I've got to put all these extra parentheses in it as well, but you'll get used to that the more you use it. So there's that function, and then I'll just type in x and the bottom one, y2, graph it, and hopefully they end up being the same thing. So here's the rational function that we started with. And then the red one is the reduced one. And they're the same, right? So would anybody have looked at this initially and thought, yep, that's the line y equals x? No, okay? Now, if I go to my table, second table, do you see any errors? No. Okay, because my x variable, my independent variable, skips over a third, right? So what I need to do to address that is go to second, and then this key right here, and it's hard to see, it says window, which when you hit second, it actually takes you to what we call our table setup, which is basically setting up those x values. Okay? And if whatever where I think the hole is, I'm going to create the change in table here to somehow incorporate that. So if my hole is at 1/3, I'm going to type in 1/3 here, okay? But if my hole was at like 7/3, I could type in 7/3, or I could type in 1/3, because it'll eventually show up there, right? Okay. Hit enter, and now I'm going to go second table, and now you see my x's changed by a third, right? And there you see your error. So at 1/3, comma 1/3 is where you have your hole. Does that kind of make sense? Mm-hmm. Now, some people don't even like doing that, which is fine. I really don't like doing that. So instead of doing the table setup, I always go down to the independent variable and ask. So highlight ask. An independent variable is what variable? That's x. So then my table, when I go to second table, my table is blank. And I set it up so that I can ask, what does it do at 1/3? Okay, and I can verify those things. Does that make sense? Mm-hmm. Now just be cautious, because it doesn't always, an error doesn't always mean whole. An error means division by 0. Okay, so you might end up with an asymptote saying error as well. Is that okay with everybody? Yeah. Okay. So those are just 3 different ways, depending on the technology that you are comfortable with, that you prefer, that you can realize or confirm your locations of your holes. Okay? Now, I'd like to get into, does anybody have questions on holes? Yes?
So if you have like a hole at, like let's say your denominator is like x and then times x minus 5, and you also have x minus 5 on your numerator, so your hole was at x equals 5, but you can still have vertical aspects of 0,
Yes.
you just can't have it of 5.
Yes.
Okay.
So the question is, if we have, let's go x minus 5 up top, and on the bottom we have x times x minus 5. So in this case, so we would have, because the x minus 5s cancel, we have a hole at, and in this case it's going to be 5 comma, so when they cancel, you're going to be left with just 1 over x, right? So 1 over x, when I plug 5 into that, I get 1/5. So there should be a hole right there. Does that make sense? Where A is. And if I ask it to find f of 5, it tells me it's undefined. So there is a hole there. So that point should be open. Okay. If this reduces, which it does, it reduces to 1 over x, right? If I look at the asymptote for 1 over x, that's when x is 0, correct? So that's why we have this vertical asymptote here at 0. If I had, I think it's just a little bit easier. I don't like when my asymptote is the y-axis. So let's go like x, like plus 3 here. So now the x minus 5's cancel. Now my hole is no longer at that point. My hole, so at 5, it'd be, so the hole shows up at 5, x being 5, but then the y value would be, what, 1/8? I reduce those, I get 1 on top. So g of x would equal 1 over x plus 3. That's the same graph. If I had x to be 5, this would be 1/8, right? So 5 1/8 is where your hole is. And then when these cancel, you're left in with 1 over x plus 3. So maybe once I look at them canceling, I can then look at this and say, well, then I'm still going to have an asymptote at -3 over here, which is what we're seeing visually, right? Does that kind of answer your question?
Yeah.
Cool. Okay, so the next thing then is kind of a little caveat of some questions, some things that happen occasionally when we do not have horizontal asymptote. If I don't have a horizontal asymptote, then I'm going to have either what we call an oblique asymptote, which is like the, we have polynomials, right? But within polynomials, we have better classifications like trinomial, binomial, monomial, right? Every monomial is a polynomial, okay? But every polynomial is not a monomial, right? Okay? Same thing happens with these slant asymptotes, okay? Every slant asymptote is an oblique asymptote, but all oblique asymptotes are not slant. Does that make sense? Slant asymptote means that it's an asymptote that is linear, but it's not horizontal, okay? An oblique asymptote is any asymptote that is not vertical or horizontal, okay? So I guess the argument is slant asymptotes are a first degree oblique asymptote, okay? And this is the argument for what happens. And remember, we're always interested in end behavior. So what happens is if we have our rational function, which is p of x over q of x, in which the degree of the numerator is 1 more than the degree of the denominator. So we're looking at something like x to the third over x squared, or x to the, essentially n plus 1 over x to the n. Okay, so where the numerator is 1 more than the denominator. Okay, because what happens, think about this, if it's x to the n plus 1, that's x to the n times x to the first, we write it as that. And then when those cancel, you're left with just x to the first, right? So what happens is through comparing the leading degrees and leading terms, you're going to cancel, and you're going to be left with x to the first in the numerator, okay? Well, that generates what we call a slant asymptote, okay? And we realize what the slant asymptote is through the division algorithm, okay? Which we took, basically we put r of x in here, and we put the divisor out here, and it's going to give us the quotient there, right? Does that make sense? And we'll have our remainder divided by the divisor, okay? And then we had alternate formats that we could put that into. And basically what happens is that we can put it into a format like this, okay? Where now they're using q of x, which is the denominator here, which that is also the divisor. If we go back to when we did long division, we were calling it d of x, but here, because it's q in this formula, they're just using q, okay? But if you wanted to say d of x there as well. But think about what happens when we want something in the long run. So the remainder, when we do long division, okay, we do our long division, we get our remainder all the way down here, and we stop the division algorithm. We stop the division algorithm when the remainder is less than the divisor, right? Okay, so let's say my divisor is like x minus 2. We're going to stop when this remainder is a degree less than the divisor. So that would give me a remainder of 8, and we'd put it over the divisor of x minus 2. Okay, now think about what happens. We're interested in when x gets really, really big, right? When x is 10, doesn't this thing become 1? When x is 100, this becomes 8 over 98, right? When x is 1,000, it becomes 8 over 998. When x is 10,000, it's 8 over 9998, right? What's this quotient tending to? It's going to 0, right? So when that's going to 0, that thing, the remainder, is unimportant to us. It's negligible in regards to what this graph is doing. That means then, whatever this part was here, which is our quotient, that was the thing that dictates what our y values are doing in the long run. Okay? So the division algorithm tells us how to find the slant asymptote. That will make a little bit more sense, I think, when we do a specific example. But that's what this is arguing here. Okay, it says this means that as x gets to positive or negative infinity, the remainder divided by the divisor goes to 0, and then all you're left with is the quotient, and the quotient then is your slant asymptote. So, here's an example, okay? I want to do this example just like any other problem, okay? We're going to approach this initially, rational function, goal is to graph it. We don't know anything about it yet, so I'm going to write my list of things down. Okay, now I'm going to augment the list from now on. Instead of just saying HA, I'm going to say HA or SA, or sometimes it could be oblique. Okay? You can't have a horizontal asymptote and a slant asymptote at the same time. You can't have a horizontal asymptote and oblique asymptote at the same time because they are going off of the same comparison of leading terms. You can't have, they're mutually exclusive events, which means they cannot happen at the same time, right? Vertical asymptotes. We're going to ask about holes. Still do x-intercepts. Still do y-intercepts. And now instead of saying cross the horizontal asymptote, I'm going to say, do I cross the horizontal, the slant, the oblique? Okay. You can, and I jump back and forth with my steps. You can either factor everything first or determine the horizontal slant or oblique asymptote first, doesn't matter. Let's just go ahead and factor because we'll need that. So what's this top factor to? X minus 5, x plus 1. And the bottom obviously is already factored. Okay? So when I want to look at the horizontal, slant, or oblique asymptote, I'm comparing those things, right? Comparing the leading terms. And because the numerator is one more than the denominator, that is the identifier that you're going to have a slant asymptote. Okay? Now, we have to determine what is that slant asymptote. So here, we're going to have to do the long division. So I'm going to take x squared minus 4x minus 5 and divide by x minus 3. Okay. Some of you that are kind of in tune to what we've been doing might say, why don't we use synthetic division? And you could, but generally, synthetic division only works for dividing by a divisor that is first degree. We could potentially, we'll see some examples of this later, have a divisor that's like x squared instead of x minus 3. And then the synthetic division process or algorithm does not work for that. So my suggestion, always do the long division like this. Okay? So now the question is, what do I put right here? So when I multiply by x, I get x squared. X. So now I'm going to distribute, and I get x squared minus 3x. I'm a person, I like to multiply by a negative, and then add straight down. Create negative x, bring my negative 5 down. Now what goes in the next spot? So I multiply by x, I get negative x. Negative 1. So negative 1 times x gives me negative x. Negative 1 times negative 3 gives me positive 3. I negate those, and then add straight down. Gives me negative 8, right? Now the algorithm says that's where you stop. You stop at negative 8 because it has a degree, which is x to the 0 right now, that is 1 less than that, right? So x minus 3 no longer divides into negative 8. So I'm going to rewrite this as then plus a negative 8 over x minus 3. Now, everything above this problem, all the theorem type explanation of why we do this, says that when x gets really, really, really big, think when x is 100, or then 1,000, then 10,000, then 100,000, then 1,000,000. If x is 1,000,000, okay, think about this. Somebody takes, you have $1 million. Somebody takes $1 from you. You now have $999,999, right? Okay. Now you add negative 8 divided by 1,000,000 minus 3 cents to that. Okay. Which is going to be removing money, right? Okay. But is that a very, 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 very small amount of money that you're removing from your million? So you still ultimately have $1 million minus 1, right? Now if you had 100 million, or 1 billion, or 100 billion, then taking that negative 8 over x minus 3 is even smaller, right? So the argument is, because we're only interested, the slant asymptote is only telling us what happens when x is huge. The argument is that this thing right here is negligible. It doesn't do anything for us when x is really big. So what is the only thing that is creating a y value for us when x is really big? It's x minus 1. Does that make sense? So x minus 1, just the quotient, that is your slant asymptote. If you said this was x cubed over x, yes, it'd be oblique. So y equals x minus 1, that's our slant asymptote. And it's slant because it's to the first power, and it's not horizontal. Does that make sense? So it's linear, but it's not horizontal. Vertical asymptotes, do I have a vertical asymptote here? X equals 3. Do you have any factors that are common in the top and the bottom? Nope, so no holes. What do you set equal to 0 to determine your x-intercepts? Set that numerator equal to 0. Okay. So then I'm going to have an x-intercept at 5, 0 and negative 1, 0, right? Y-intercepts, the way I always do it is I go try to find the C term, or I don't want to say C because it might not be, it might be a D term or whatever, depending on how many terms are in your polynomial, but I always go look for the constant terms in the polynomials, the numerator and denominator, and divide up. So what's negative 5 divided by negative 3? Positive 5/3, right? So when x is 0, because that's what, if x was 0, that'd go away, that'd go away, that'd go away, right? And that's why you're left with negative 5 compared to negative 3. Okay? So we can plot all that stuff, that's good. Now the question is, 1, why do these things keep popping up? There you go. Do you cross the slant asymptote? So what we're going to do, because remember, this is the thing that we're trying to graph, right? So we want to see, does that cross your slant asymptote? So you're going to take those two things and set them equal to each other. And I always, whenever you're trying to determine whether you cross something, use the expanded version. So x squared minus 4x minus 5 over x minus 3 equals x minus 1. If I'm going to see if these cross, or determine if they cross, what is the first step? Multiply by x minus 3. Multiply by that LCD, right? So that's going to give me, on the left, just x squared minus 4x minus 5. And on the right, it's going to be x minus 1 times x minus 3. Now to solve this, you actually have to expand this, because there's some hidden common terms here, right? So x squared minus 4x plus 3, right? What happens to this x squared on the left and this x squared on the right? Cancel. What happens with the negative 4x and the negative 4x? Cancel. And you're left with negative 5 equals positive 3. And that's false. And a false statement tells you what? No crossing. Okay? So if there's no crossing, then we have all the information we need to graph this thing. We have a slant asymptote at x minus 1. So we come down here to negative 1, and up 1 over 1. So there's our slant asymptote. We have a slant asymptote, or sorry, a vertical asymptote at 3. X-intercept at negative 1. Y-intercept at 0, 5/3. And then over here, we've got another x-intercept at 5, right? Now, because I never crossed the horizontal asymptote, or sorry, slant asymptote, I'm going to treat it just like a horizontal asymptote. Does that make sense? So as I move to the left, from this point here to the left, you have to start getting closer and closer to that asymptote, but you're not going to cross it. I go through that y-intercept, and then as I go to the right, I'm going to get closer and closer to that vertical asymptote. Does that make sense? Okay. Now over here, same idea. As I move to the left, which direction is that graph going to have to move? Can I go up? If I go up, I'm going to cross a asymptote that I've got the work that says you never cross it, right? So as I move left, I got to go down. And then as this goes to the right, it will eventually get kind of sucked up to that slant asymptote. If we graph this real quick, just because I think my graphs by hand aren't all that convincing because of the scale. Go x squared minus 4x and the human error minus 5 over x minus 3. I'm going to graph x equals 3 graph x minus 1. Would you guys agree? Okay, so if those black lines are my asymptotes, this is my vertical asymptote. There's my slant one, is the purple. Travel along that slant asymptote. Okay, we'll pick up there tomorrow. See ya.